The topic of fluoroscopy. Okay, that's fine. So things will hopefully be close, God willing. The topic of fluoroscopy, in simple terms, is that the most challenging or cumbersome aspect is the image intensity file. As you all know, the function of fluoroscopy and its applications. In cases like cardiac angiography, for example, in diagnostic procedures, or even stenting or catheterization, and its function in interventional radiology, as well as its role in the operating theatre, such as in the installation of prostheses or orthopedic procedures, is quite extensive. In fluoroscopy, I rely on two things. What do I want from fluoroscopy? As we discussed in mammography, what is my target? When I set up the mammography machine, I would see what I want from the machine and then set my specifications or the properties of my machine that will lead me to my results or output. The same idea applies to fluoroscopy. I want a machine that does two things. The first thing it should give me is an image, and this image will help me with something very important, which is to see a dynamic image, meaning a continuous image with me. I am not just taking a spot image. Yes, I can take a spot image. So, are you with me? I don't take spot images. Yes, I can take a spot image, but in most of my work, or in the application, or in the utilization, or if I'm working in procedures and I have a patient and I want to do an injection, for example, with a certain contrast, and I want to see if there's a wire in the patient or something and I want to track it, I take a lot of spots. Sometimes I do continuous exposure to give me a dynamic image. A dynamic image means that in continuous exposure from the radiation, you need the image that comes out to provide you with high resolution information. At the same time, you will overload and tube load on the poor X-ray tube. In this case, your focal spot size will not be like that of mammography. You don't need the same resolution as mammography, but you need a small focal spot size, not a large one. To reduce the overload, especially when using continuous motion, I think that the milliampere should not be high, and this is indeed what happens in fluoroscopy cases, for example, around 5 milliampere if you use dynamic or continuous exposure. Why? Because you do not want to overload the tube. There will also be a challenge. And what is the problem? The translated image coming from the patients will either be preliminary or will be large. So you need the detector to be different from the regular detector or to have slightly different technology. Therefore, you need your detector to be what should be different from the regular one. Especially since, as we said, we want to detect low energy or low X-ray photons, particularly in dynamic cases or in cases of continuous motion. And in the end, this image will be displayed on a video screen. Or even if you want to place it, for example, on a screen where I can display a video, I can see my image while I am working. I can set it to see it clearly. I can specify, for example, how many milliseconds I want a specific image in a certain mode, whether it is a specific mode or not, and see my image, or even if I want a specific image, I can do that. The detector is a story all about fluoroscopy. The detector is the image intensifier. The word intensifier means something that increases intensity, as its name suggests. It is true that I am working on something, that if you want to increase your intensity, if you receive your intensity, it will be your intensity. That's why it's called an intensifier. I am doing something called intensification, which means I increase intensity. So how is this done? It is done in a distinctive way. It is done in a distinctive way. I have, for example, an X-ray tube and a patient, and I want to send across the X-ray. Now, the idea is that to achieve intensification, you need to think about receiving the X-ray that comes out on something such as a surface or a medium. This thing converts the X-ray photon into a light photon. or something else that you can control and intensify or increase its brightness or intensity. So, what are we going to do? We are going to get our image intensifier. We create it and place it on the exterior, and we make it from a material such as aluminum. Why? Because it is important that nothing from the outside enters, but it allows a bit of scattering so that the X-ray photons can enter through the input window, which is the primary input window. Then it is received by something, so I will get something that is the input phosphor. What is phosphor? It is the scintillator material that interacts with the X-rays to produce light photons. Now, the X-rays entering have a certain energy. For example, if we are working in the range of 120 kilovolt, the X-ray coming from the tube will have a maximum of most of the photons. So we are talking about a range, for example, of 30-40 kilovolt. Okay, great. The material that I will make the input phosphor, or the screen that will receive the X-ray photon, must be specifically specified. It has an attenuation property, or a characteristic in the absorption of this energy, which is distinctive. For example, I shouldn't choose a material with a K edge that is significantly different from the energy range I am working in. It needs to be close. So they told you that you have cesium iodide. As we mentioned before, 33 kilo electron volts means that the nearby range will cause significant attenuation, and cesium, which is at approximately 36 kilo electron volts. So I will create a phosphor input here in this way to receive the X-ray photon from cesium and convert it into light. This light can spread in various directions, which will reduce my resolution, as we have thoroughly discussed earlier. The diffusion that occurs allows for localization. It was mentioned that cesium iodide has the property of being like a needle, as we talked about before, in the form of needle tubes like this. When a light photon is generated, these needles help it travel along this path without experiencing diffusion. So, we have converted one light photon from the X-ray that hit the cesium iodide, resulting in 1,000 photons. That's great. So that's it. We've dealt with the issue of what happens or what will happen as a result of choosing the right type. Great, now take this. He said, no, what you just mentioned is still not enough for us. So what should we do? He said, all right, you will take these and add another material. So what he calls cesium antimonide here receives the incoming light photon and converts it into an electron. So why did he actually tell you that if I could indeed control this electron, I could essentially focus it and gather them together? Then I could strike these focused electrons onto the output phosphor here, meaning onto a small screen that is relatively sized compared to the input screen. It's as if you are basically doing minimization and focusing at the same time. The image that will come out from the input phosphor will not just be minimized, you will also enhance it. More brightness means more clarity and higher light intensity, which leads to greater magnification. Brightness is essentially the amount of light emitted or reflected by an object, and when this brightness increases, it enhances the clarity of the image being observed. Higher light intensity refers to the concentration of light energy in a given area, which contributes to the overall brightness and clarity. The larger the magnification, the more you are effectively collecting a greater number of electrons, which will give you a higher output when you strike the phosphor. Magnification is the process of enlarging the appearance of an object, and as magnification increases, it allows for a more detailed observation of the object. The larger the magnification, the more electrons are collected, which enhances the image quality. The light intensity that will come out of the phosphor is relative to the X-ray that was initially input. The intensity of the light photon that comes out of the phosphor depends on the number of electrons present here, which have undergone focusing and aggregation to impact the phosphor output. Focusing and aggregation are processes where electrons are directed and concentrated to achieve a desired effect on the phosphor. So how do we collect the electrons generated by your photocathode? To collect them, there are three types of electrons here that are graded in voltage. They provide energy. These electrons are categorized based on their energy levels, which determine their ability to contribute to the overall process. Each type of electron plays a specific role in the energy transfer process, and understanding these roles is crucial for optimizing the system's performance. What is the kinetic energy for? It's for the electrons to move with it. They undergo excitation and move with it. At the same time, I will place an anode here. This anode has a voltage difference between it and the cathode that ranges from 25,000 volts to 30,000 volts, which is very high and powerful. What does this do? It makes all the electrons go towards the anode and gather, and they get focused. Now, what is this anode like? It's like a donut with holes in it, so that after it gets focused and gathers at this point, it starts to diverge like this and begins to fall onto the output phosphor, which is cadmium zinc sulfide, whose attenuation is very suitable for the electrons. So, it starts giving me light photons. Now, these light photons begin to be received on something called optical length on a specific lens. This optical length starts to transmit the light that translates my image into video, and on another screen, it appears to you as if it were a film. Let's take a look at this so you can visualize it. Here is the X-ray hitting our window, and then we have the input phosphor, which is cesium iodide. After that, you will find the cesium iodide, and it starts to emit fluorescence. It meets the photocathode that is present to convert it into electrons. After the electrons are generated, they undergo focusing, which we discussed, through the high voltage difference between the anode and the cathode. Then, they fall onto the output phosphor, which is my cadmium zinc sulfide. The property is suitable for the electrons that fall on it, and it starts to give me light, which will then come out and be received by my camera, okay? This is the shape of the phosphor input. These are the characteristics of the phosphor input. I have performed a minimization of the image. So what is this minimization based on? It is based on the input diameter of the phosphor and the output phosphor. What does that mean? It refers to the ratio between them. For example, if you have a very large phosphor input, its field of view is very large, right? In comparison, the minimization you have done is significant. So the ratio between the diameter of the input phosphor and the diameter of the output phosphor, the whole square, I call it the magnification gene or magnification gene. Okay? The size of this magnification or the magnification gene increases when the difference between the input and output increases. The diameter of the output diameter, what does that mean? It means that if you reduce the input phosphor, it indicates that your magnification has decreased, which means that the number of light photons generated from the input phosphor has decreased. Consequently, the number of electrons emitted from the photocathode has also decreased. This means that the light photons coming from the phosphor room have decreased. Therefore, if the diameter decreases, or if your field of view decreases, you have effectively reduced the brightness that will occur. You have reduced the size of the brightness that will happen. This is because brightness depends on the number of light photons generated and the photoelectrons, which in turn reduces the exposed area for the X-ray. Thus, it follows that the photoelectrons and light photons generated all contribute to the decrease in your brightness. So, the process of reduction that is happening, or what I call the reduction in your field of view, is referred to as magnification. In the image you are inspired by, you want to do something called electronic magnification. You want to increase the resolution a bit. How to increase the resolution then? So, by adjusting the voltage values that affect the electrons generated by the photocathode, you can achieve better focusing and reduce the diameter of that area or region. In this case, it's as if you are increasing the resolution of the image, but it will come at the expense of the number of light photons that you were originally producing, which decreases. Therefore, the magnification here Just as I am currently working with two different fields of view, one large and one small, I add the large field of view and the small field of view. Which one of them has more minification? We said the ratio between the two diameters. For me, which minification gain will be higher? The large field of view will have a higher minification gain for me. This will give you more, right? The second will have a lower minification gain. The minification you did has a lower gain compared to the large field of view. So, which one will give you a higher special resolution? The smaller field of view will give you a higher special resolution than the large field of view. Now, which one will cause you more problems with the image? The large field of view will have higher image distortion. Why is it higher? We will talk later about some artifacts that will result from your field of view. When the brightness in the output phosphor decreases, to compensate for the reduced brightness, what needs to be done? The parameters need to be increased. Increase the kV and increase the milliampere. If you increase these parameters, have you increased the dose to the patient or not? You have increased the dose to the patient. In the case of minification or electronic minification that occurs, you have increased the dose to the patient, increased the resolution, and decreased the brightness. If you use a large field of view, you will be more exposed to image distortion and the existing artifacts. The special resolution is less than the topic of magnification or less than the topic of field of view, but the magnification is significant and the radiation dose is lower. Therefore, it advises you to reduce the use of magnification as much as you can, because it has a significant impact on increasing the dose through automatic brightness control. It places a sensor at the output phosphor, and as soon as it detects a low light intensity, it starts connected to a circuit with the X-ray system to inform it about your parameters, similar to the automatic exposure control. But here it is called brightness control, because it is related to the amount of brightness that occurs. We mentioned the ratio between the two diameters, which I referred to as the minification gain. The ratio between the number of light photons that are emitted at the output phosphor and the X-ray photons that enter at the input phosphor is called flux gain. So now, here are the X-ray photons entering at the input phosphor, which I referred to as flux gain. The X-ray entered the input phosphor and exited to the phone, hitting the photocathode and producing photoelectrons. The focusing occurred in this manner, and the ratio between the output phosphor of the phone and the X-ray photons at the input phosphor was termed flux gain. Now I have two things, flux gain and minification gain. If the number of light photons generated at the first input phosphor increases, will the brightness increase or decrease? It will increase. So, I have a new term called brightness gain. Brightness gain is defined as the flux gain multiplied by the minification gain in direct proportion. This means that an increase in either one will increase the brightness gain. Therefore, brightness gain depends on the product of flux gain and minification gain. However, brightness gain cannot be measured directly. There is no way to measure it. So, how can I measure it? There is something called the convergence factor. The amount of luminescence you received at the dose that the entrance dose entered for the patient can be determined using an ionization chamber on the patient, and you can know the exact dose that was precisely reached at the skin. What is the entrance dose? Exactly. So the convergent factor remains after 1 second. Well, when I perform calculations at this level, it's indeed easy to perform calculations. Even on some screens, you can, in fact, perform calculations of the level from the display monitor itself. With specific types of devices that are designed for this purpose and can measure the display against the entrance dose rate. This leads you to a conversion factor or gives you management over the amount of brightness present. By the way, we often forget the amount of lighting, which is measured in candles per meter square. The entrance dose, which is the dose rate, is measured in microgray per second, milligray per second, or gray per second, depending on the amount of dose present. The dose is always measured in gray, which gives you an indication or information about the dose, as we will discuss later regarding effective dose, absorbed dose, and equivalent dose. These are all units you often hear about, like millisievert and milligray. You often hear the difference between milligray and millisievert. Millisievert always represents something called effective dose. You should also know that we will discuss the dose, concerning the patient and the staff. I have 4 things. One is called exposure dose, and there are other factors. The amount of energy absorbed by a unit of mass is called absorbed dose, measured in joules per kilogram, which is referred to as gray. Now, what type of radiation is this? Is it when exposed to X-rays, as when exposed to alpha particles, beta particles, or neutrons? There is a difference. This difference is due to the effect of the type of radiation. Alpha particles are among the most impactful types because they lose all their energy in a very short range. They are called high linear energy transfer because the amount of energy they carry is transferred entirely in a short range, in millimeters. If someone is outside, they shouldn't worry. But if it enters their body, they should worry because once it enters, it deposits all its energy in one spot, which could lead to damage or an effect that is 20 times that of X-rays and gamma rays. So this 20 is a factor. Therefore, we consider the type of radiation when calculating equivalent dose, which is obtained by multiplying the radiation weighting factor. As for effective dose, it can affect the ovaries, the brain, the skin, or various groups. This is important to understand because the impact of radiation can vary significantly depending on the type of tissue or organ that is exposed to the radiation, which is crucial to understand.